here we'll take one example for POS tagging with hidden Markov model. So first of all, this hidden Markov model, as we already know, it is a stochastic technique for POS tagging. So hidden Markov models, they are used in various applications, like you can use it in reinforcement learning and even temporal pattern recognition. Like it can be either speech, handwriting, gesture recognition, or musical score following, bioinformatics, etc. So before going to this example, first we must know difference between transition probability and emission probability. So what is this transition probability? Say suppose here you can observe in the slide there are total three. So here you can see three types of tags. One is noun, then modal, and then verb. So here we need to first know how likely it is, how likely the noun is followed by modal and the modal is followed by verb, right? So the transition probability can be defined as it's a likelihood of a particular sequence. For example, if you take example is how likely that a noun is followed by a modal. So noun followed by modal. So in this example, you can see noun followed by modal. So you need to check how many times we are getting that sequence, and modal followed by verb. So that means M followed by V, and then V followed by N. So we need to find out likelihood of this sequence. So it should be high for a particular sequence to be correct. So we can define this transition probability as the probability that connects change from one state to next state in the system. Coming to emission probability, so it is the probability that quantifies possibility of making a particular observation given a defined state. Say suppose in this example, so here we need to find out how many times Jane appeared as noun and how many times Mary appeared as noun. Okay, so if you take a sentence like I love artificial intelligence, then in that case I would be a pronoun. So how likely that a word I would be pronoun or the word love would be verb, the word artificial would be an adjective, and the word intelligence would be noun. So you need to find out that likelihood. So these probabilities, they are called as emission probabilities. So here in this example, we need to find out how likely Spot would be noun, Will would be modal, C would be verb, Mary would be noun. So that gives you emission probability. So now let us move into our example. So here first take this. These are the set of sentences. And from this, first we need to find out or we need to assign tags for every word in the given sentence. So see here. So how many sentences we have in this? Total 4. So first take Mary. So take Mary, and if you take the first sentence, that can be divided into 5 tokens, right? So for every token, you need to give one tag. Similarly, the second one. So give tags. So here we need to use 3 tags, that is noun, modal, and verb. And after this, here you can see that Mary appears 4 times as noun, right? So from this, first you need to calculate the emission probabilities in order to create a counting table. So in this, you can see this counting table where first you need to find out total number of words in the given example. So here in this example, you can find out total number of words. So we have Mary, Jane, Ken, C, Will, 5, and this Spot is 6. Then again, Pat, 7. So total we have 7 words. So don't take repeated words again. So take those 7 words and The three tags which we used are noun, modal, and verb. Now you need to check how many times Mary appeared as noun. So from this you can find out. So Mary appeared as noun 1, and here it is 2, and this is 3, and this is 4. So Mary appeared as noun 4 times. So this value will be 4. Now check how many times Mary appeared as modal. So in all the 4 sentences, Mary appeared as noun only. So modal will be 0 and verb will be 0. Similarly, check how many times Jane appeared as noun. So here you can see Jane, noun 1, and Jane, noun 2. So this value will be 2. And modal and verb, that combinations will be 0. And then will appeared as noun. So how many times will appeared as noun? 1. So in the remaining 3 cases, will appeared as modal. So here, will appeared as noun once and will appeared as modal 3 times. And will appeared as verb is 0. In this way, for every word, you need to find out number of times that word appeared as noun, modal, and verb. From this, we can calculate this table. So after getting this, you need to find out or divide each column by total number of their appearances. For example, if you take this first column, so find out sum of this column values. So you can see 4 plus 2 plus 1 plus 2. So it gives you 9. Similarly, for the second one, 3 plus 1. So it gives you 4. And the third one, 2 plus 1 plus 1, that is 4. Now, you need to divide every value by this total. So that gives you emission probability. So the first case will be 4 by 9. And the second one divided by 9, 2 by 9. Third one divided by 9, 1 by 9, 4, 2 by 9. Similarly here, divide 3 by 4 and it will be 1 by 4. And the last one, verb, divide 1 by 4, sum of the column values, 2 by 4, and here it is 1 by 4. So this is nothing but emission probability. So you can see that in the next slide. So the thing which we did just now in the previous slide is represented like this. That is the emission probability. And after this, you can see that the probability that Mary appeared as noun is 4 by 9. So these are probabilities, emission probabilities. And here we have to calculate the transition probabilities. So for that, we need to define 2 more tags. See, in this example, here in the slide, you can see transition probabilities. So first, we have to calculate the transition probabilities here. So for that, we are taking 2 more tags, that is S, start, and here we have end. So S is usually placed at the beginning of a sentence, whereas E, that is end, which should be placed at the end of a sentence. And now you need to create a table from this. That becomes your transition probability table. So take the start word followed by POS tags, that is noun, modal, and verb. And here you can take noun, modal, and verb followed by end. Now our task is, so you need to check how many times we have the sequence SN. That means how many times a noun appeared as the first entry. So here you can see from this example, noun, how many times it occurred in the first place. Noun, noun, and noun. So 3 times. So this value is 3. Next check start followed by modal. So how many times modal appeared at the first entry? It occurred only once. So this value will be 1. Whereas remaining verb and end, they have not appeared anywhere here. So it becomes 0. Now check noun, noun sequences. So check this. Noun, it occurred once here. And you can see no other place. So we can't find out this noun sequence in remaining sentences. So this is only one. Next, noun verb. Sorry, noun modal. So noun modal combinations. So you can find it here, noun modal. Then this is noun modal. And here we have noun modal. So how many combinations? Total 3. Now noun verb. So where we have noun verb sequence? Here. So we have only one possibility. So that becomes 1. Noun followed by end. So how many times we got noun at the end? So here 1, 2, 3 and 4. So this value will be 4. In the same way, you can do it for modal noun combination, modal. Similarly, verb noun combination, verb modal and so on. So from this, you'll get this table. So in this table, again, we need to calculate some of the values. In our emission probability table, we calculated some of the entire column and divided that value. Whereas here, you need to calculate some of the complete row values. So here you can calculate some of this row values. 3 plus 1, that gives you 4. And here it is 1 plus 3 plus 1 plus 4, that gives you 9. Here it is 1 plus 3, 4. And the last row also it gives you 4. From this you can derive this table. So here take the same table and instead of 3, you need to replace 3 with 3 by 4. Divide 3 by 4. Similarly, 1 by 4. And second row value is 9. So divide every value in second row by 9. And the third row, it gives you 4. So divide every value in the third row by 4. And the fourth row also, it gives you total as 4. So divide every value in fourth row by 4. So from this, you will get this table. So in this way, we can calculate transition probability and emission probability. And then let us take a sentence now. And here, Will can spot Mary. So we just tagged this sentence as, so we are assuming Will as modal, Ken as verb, spot as noun, Mary as noun. So we are taking this sequence randomly. Now we need to calculate the probability of the sequence being correct by using the following technique. So you can see this in the diagram. So you need to take what are the words present in the given sentence. So we need to tag them with wrong tags, right? So we are just assuming these tags in order to tag the given sentence. So first take the words in the given sentence. Will, can, spot, Mary. Now you need to find out transition probabilities and emission probabilities. So we already calculated transition and emission probabilities from the table. You need to create this, right? So first, these values, they represent transition probabilities. So start followed by modal, modal followed by verb, verb to noun, noun to noun and noun to end. So check this probability value, start to modal. So where we have start to modal is 1 by 4. So this value will be 1 by 4. Now take modal to verb. So this is modal to verb. So it gives you 3 by 4. So here this value becomes 3 by 4. Now verb to noun. So this is verb and this value is noun. Verb to noun is 1. So this value will be 1. And then noun to noun. So you can see noun to noun is 1 by 9. So this will be 1 by 9. Then noun to end. So how many times noun appeared at the end? Noun to end is 4 by 9. So this is 4 by 9. So you just take the values from the table and replace the values here. Now, these values, they represent emission probability. Okay. So that means how many times will appear as modal. So you can go to emission probability table and find out how many times will appear as modal. So here it is, probability is 3 by 4. So enter this value as 3 by 4. How many times can appeared as verb? That is 0. How many times spot appeared as noun? Go to the table, check spot appeared as noun. That gives you 2 by 9. So this value is 2 by 9. Next, check how many times Mary appeared as noun. So where is Mary? Mary appeared as noun. So total it is 4 by 9. So in this way, we need to calculate the probability of the sequence. So after drawing this picture, you need to multiply the values. So multiply 1 by 4 into 3 by 4 into 3 by 4 into 0, then 1 into 2 by 9 into 1 by 9 into 4 by 9 into 4 by 9. So as we are multiplying this value by 0, it gives you result 0. So when these words are correctly tagged, so usually we get a probability greater than 0. So now let us calculate the product of these terms by using a second sequence. So let us take one more sequence because we got 0. So we are trying with one more sequence. So in this case, Will is treated as noun, Ken is treated as modal, or Spot is tagged with verb, and Mary is tagged with noun. So in our previous case, we took a different sequence. Will is treated as modal, whereas here Will is taken as noun. So let us try for this sequence. So just like how we calculated the value before, you need to calculate the tag sequence probability by multiplying all the values. Here we got some value like this, 0.00025. So in this way, here we just have 3 tags, but we'll get more number of possibilities. So how many possibilities can we get? So that we can calculate it like this. So total number of words in the given question, Will can Spot Mary. Total number of words are 4. And how many tags we used here? Total 3, noun, modal and verb. So this value becomes 3 power 4. 3 power 4 means there are total 81 possibilities. Right? So 81 different combinations of tags can be formed from this. So you can just see all possible combinations with 3 tags. So this is the image, or this is the diagram which we get if you tag all the, or if you represent all the sequences. So here you need to represent transition probability, and this is your emission probability. So transition probabilities are not represented in this diagram because it becomes more clumsy. So, but internally the representation is like this. So you need to include both the transition and emission probabilities with the help of the table. Now the next step is, so here you can see there are total 81 different combination of tags. So number of tags used are 3 and number of words used to tag are 4. Total 4 words in the given example. So that probability gives you 3 power 4, which is 81. So the next step is you need to delete all the vertices and edges with the probability 0 and also the vertices which do not lead to endpoint. So in this diagram, you can see some of the vertices or edges, they are having probability as 0. So if you see this one, here you can see 0. Similarly, here also you can find value as 0. And in this node, again we have 0. So you need to remove all those things. So once you remove everything, then you will get the representation like this. So now there are only two paths. Earlier there are total 81 combinations, 81 paths. Whereas here, after removing vertices and edges with zero probability, we got only two paths. And for these two paths, again, we need to calculate the probability. So that can be done like this. See, 3 by 4 into 3 by 4 into 1 by 9 into what is the first path? This one. 3 into 3 by 4 into 1 by 4 into 1 by 4 into 2 by 9 into 1 by 9 into 4 by 9 into 4 by 9. So we are reaching end point here, right? So that gives you this first sequence. So what is the sequence? Start, noun, modal, noun, noun, and end. And the second sequence give you start, noun, modal, verb, noun, and end. So here it is. This should be verb and this should be noun. So just make those corrections and it gives you total value. So from these two parts, again, you can find out the probability. You can check this. The probability of the second sequence is much higher when compared to the previous one. So HMM is going to tag each word in the sentence according to the sequence. So we'll use this second method or the second sequence in order to tag each word in the given sentence, as this is having higher probability. And you can even optimize this HMM with Viterbi algorithm. So in a previous example, that is in our previous slide, we saw, so we optimized HMM and brought our calculations down from 81 to just 2. Now we are going to further optimize the HMM by using Viterbi algorithm. So let us see how to use this. So first consider the vertex encircled in the above example. So this is the vertex which is encircled, right? So there are two paths leading to this vertex. You can see we have one path from here and the second path is like this. There are two paths. So now we are actually concerned with the mini path having the lowest probability. So the same procedure which we considered or which we done till now for all the states in the graph. So you need to use the same procedure. So the probabilities of all the paths leading to a node are calculated and we remove the edges or paths which have lower probability cost. So here first we need to calculate the probabilities. So take the two paths. So write them separately like this. And if you calculate the values, you will get 0.00 something and 0.00130. So if you calculate these values separately, say suppose we are taking transition probability and emission probability is 1 by 9. So 3 by 4 into 1 by 9, it gives you 0.08. Then calculate 1 by 9, 1 by 4 into 3 by 4, that gives you 0.19. And 0 into 0, that gives you 0. So in this way, we'll give values for every path. So some nodes, you can just see that some nodes having the probability of 0. So here you can see this node is having probability 0. Similarly, you can see this node is having probability 0 and such nodes have no edges attached to them. So if you observe, as this node is having probability as 0, we remove the edge here. So there is no edge, right? And also this is having probability 0. So you can remove this edge also. So the representation will be like this now. So there won't be any outgoing edge or incoming edge for the node which is having probability value as 0. So the graph which is obtained after computing probabilities, so that graph will be like this. So after calculating all the paths. So you can find out the nodes which are having 0, there is no path for those nodes. After removing all the paths, now you can see. So here to get an optimal path, we need to start from end and trace backward. So since each state has only one incoming edge, so this gives you path like this. So after removing all the nodes which are having probability value as 0, you'll get only single path. So that path is this one. Start, noun, and here it is verb, noun, and end. So before, in our previous example or in our previous case, without using this Viterbi algorithm, we even saw the edge from noun to noun also. But here we removed that. So we optimized the path or graph even. So we optimized it in a better way. So here, instead of having two paths, we are just having only single path. And this is your final graph. So you can use this sequence in order to tag the words now. So finally, the words, so here finally the words will be tagged with noun, modal, verb, and noun. So what is our question? Our question is, you can spot Mary. So will be tagged with noun. So will be treated as noun, kin as modal, verb, spot as verb, and Mary as noun. So these are the right tags. So from this, we can say that the model can successfully tag the words with their appropriate POS tags.